everyone, welcome to InsightsByRish. In today's video, we are going to build a wine quality prediction project, and here in our target feature, we have three categories: class 0, class 1 and class 2. And each class maps to a cultivar, that is cultivar 0, cultivar 1 and cultivar 2. Now this cultivar term actually refers to different grape varieties that have been cultivated to produce the desired wine, and that is what we have to predict. So we are going to use the inbuilt dataset of wine from the scikit-learn library, and let's start building the project. First, we will import all the required libraries here. I will say import pandas as PD, and then we also require the dataset from scikit-learn. So I will say from sklearn.datasets, we require this load wine dataset. Let's run that. Now we have to load this dataset into a variable. So let us say that as wine, and we will say load wine. Let's run that. Now unlike your normal datasets, you cannot directly display the columns here. You have to build your data frame out of this. So when you just say wine, it will just give you some messy data here. So you have to actually build a dataset out of this, and for that first we have to check what all data we have into this particular wine variable. So for that we will say dir wine. Let's run that. So these are all the fields present in the wine. We have to build the dataset now using all these fields. So first we are going to build our input dataset, and let us name it as x. X is of type data frame, which will store all our input data. So I will say pd.dataframe, and here I will pass the actual data, the data variable from wine. So I will say wine.data. Now this data have been passed to the data frame, but it should also have some column names. You don't have to give the column names manually. You already have that stored into the feature names. So you have to just say your columns is equal to wine.feature names. So let's run that, and now let us try to display our dataset here using the head method. As you can see, we have the data now, and also we have the column names. This is our input data, and depending upon all this data, we have to predict the wine quality, or you can say wine cultivar. We also need to check the dimension of this dataset. So it's a very small dataset, just of 178 rows and 13 columns. Now similar to this, we also have to build our target feature, that is our output feature, and to do so I will say the variable y. Now this variable y will be also of type data frame. Fine. So I will say pd.dataframe, and here I will pass the target, this target into this data frame. So I will say wine.target, and then the columns. Now here you don't have to provide anything like feature names or something like this in your data frame. You just have a single column here, so you can randomly just give any column name here. So let me say the column name should be the target. Fine. Let's run that, and let us try to display our dataset. So this is our dataset. Now we also need to check that what all fields or what all unique values we actually have in our target column. So to do so, I will say y target dot unique, and let's run that. So the unique values from our target is 0, 1 and 2. As I said previously, they are the various grape varieties that are cultivated to produce the wine. Or if you even want to check the names, you can do so. You have something called target names in your wine when you loaded your dataset, so you can just make the use of that to check the names. So I will just say here wine.target names, and let's run that. As you can see, it will give you the description of that categories, but it haven't helped us much because it has just added the word class before the values. So this will give you a more broader description about the categories here. Fine. Now the next thing that we have to do here, we require data normalization here. But before doing that, first we'll perform the data cleaning here, and to perform the data cleaning we have to check whether this data set consists of outliers or not. Now to do so, you make the use of Seaborn box plot. So let us start building the box plot here. So I will say import Seaborn as SNS. Let's run that, and SNS dot box plot. Now here we have to provide the desired field for which you have to check the outliers. So let's say the first column that I will provide here is alcohol. Let me supply it here. Let's run that. So this is your box plot for the first column, and as you can see, this particular column doesn't have any outliers. But if you continue doing this for individual columns every time, it will take a lot of time. So in order to reduce the time, we can supply all the columns in a single attribute here or in a single parameter here. Fine. And to do so, what we will do before this, we'll just display the column names. So x dot columns. Let's run that, and these are all the column names. Let us copy that. And here we'll remove this. We require one more square bracket here, and then we will provide all the column names here. And let's run this. Now as you can see, we have got the box plot for all the columns, but they are overlapped onto each other. Hence we need to increase the size of the box plot. And to do so, what I will do, before this particular cell, I will import matplotlib here. So import matplotlib dot pyplot as plt, and then I will say plt dot rc params. Here I will say figure dot fig size, and you can provide your figure size here. So I want my x-axis, that is the plot on x-axis, to be 23 and on y-axis to be 7. Let's run that, and we'll again rerun this cell. So as you can see, the size of your box plot has been increased, though the font has been reduced, but you can still zoom in and check for the column names here. So wherever you find the circular patterns, like you are able to see in the malic acid or ash column, then the magnesium column, the alkalinity of ash column. So wherever you find the circular patterns, assume that or consider that that particular columns consist of outliers, and wherever you don't find that patterns, then that particular column doesn't have any outliers. So here we have to handle the outliers for the columns malic acid, ash, alkalinity of ash, magnesium, and then few more. Fine. So in total we have 1 2 3 4 5 6 7. We have total 7 columns for which we have to handle the outliers. Now we have multiple methods to handle the outliers or to replace the or to eliminate the outliers, and they are z-score, standard deviation method, percentile method, IQR method. But we are going to make use of IQR, that is the interquartile range method, as it's an efficient one and also it's less time consuming. Fine. So we'll say quartile 1 is equal to np.percentile. So np is actually numpy. We require the numpy library here. So let me import that. And then I will say here percentile. I will pass the first column. Now here you have to handle the outliers or by providing one column at a time. You cannot provide all the columns here. You just have to handle the outliers one by one. So I will say X malic acid, and then the quartile 1 consists of 25% of your data, and interpolation is equal to midpoint. The same thing we have to repeat again for quartile 3. I just have to change the data content from 25 to 75, and then the formula of IQR, which is quartile 3 minus quartile 1. Let's run that, and we have this error, but it's none of our use. That's a basic description error. So if you want to remove that, you can just say import warnings and then warnings dot filter warnings. And then say ignore. Fine. Now the error has been removed. Now you also have to give the threshold values here. Just say your lower bound or your lower threshold is equal to quartile 1 minus 1.5 into IQR, and your upper bound or upper threshold is quartile 3 plus 1.5 into IQR. Let's run that. And let us check the value of lower bound and upper bound here. Lower bound is a negative 0.58 and the upper bound is 5.255, which means in your malic acid column, wherever you have an instance where the value of malic acid is lower than negative 0.5 or greater than 5.25, then that particular instances will be considered as an outlast and will be removed or eliminated. Fine. So what we will do, we will create a new data frame here of same name X, and here I will say I only want to include the instances between the range of negative 0.5 to 5.25. Like I don't want any instances above the value 5.25 and below the value negative 0.5. Fine. So for that I will say X malic acid, the value of malic acid should be lower than upper bound and the value of malic acid should be greater than lower bound. Let's run that and let us check the shape of our new data frame. So as you can see, initially you had I think 178 rows and now you have 175 rows, which means 3 rows have been eliminated. Fine. So this was the procedure of handling the outlast from a single column, that is your malic acid. In similar way, you have to handle the outlast for all other columns as well, wherever you find that circular patterns in the graph. So I will repeat the same thing for the ash column as well. I will just change the column name from malic acid to ash. And then I will also provide this lower bound and upper bound formulas here. Let's run that and let us check the value of lower bound and upper bound here. So the lower bound value is 1.69 and the upper bound value is 3.07, which means wherever in the data set the value for the ash column is greater than 3.07 or lower than 1.69, then that particular instance will be considered as outlast and will be removed. So we again will perform the same thing here. I will just change the column name from malic acid to ash here as well. Let's run that and let us again check the dimension here. So as you can see, 3 more rows have been reduced. The same thing we will perform for the other columns as well. The next column that we have here after ash is your alkalinity of ash. So I will just copy it from here. Let's run that and let us check the values of lower bound and upper bound here as well. So the lower bound value is 10 and the upper bound value is 28, which means wherever in your data set in the column of alkalinity of ash, if there is a value greater than 28 or lower than 10, then that particular rows or instances will be considered as outlast and will be removed. So again we will consider this and let us change the column name as well. Let's run that and let us check the shape here. So now the rows have been reduced. So now next column that we have for handling the outlast as the magnesium column. So we'll perform the same thing here. The column is magnesium. Let's run that and let us again run this particular cell. I think now you have an idea of how the lower bound and upper bound has been calculated and how we consider the outlast depending upon those values. So I won't repeat the same thing again. Let me just change the column name from alkalinity of ash to magnesium. Let's run that and let us check the shape here. Fine. So the shape or the rows have been reduced more. So the next column here after magnesium is proanthocyanins and we have to handle the outlast for this particular column. So let me copy the column name from here. And here we have to perform the same thing actually that we performed here. I will just replace the column name from magnesium to proanthocyanins. Let's run that. And even this code snippet remains same. Then I will also change the column name here. Let's run that. Let us again check the shape of our data set. Initially we had 167 rows and now 2 more rows have been reduced. After proanthocyanins, the next column that we have for which we have to handle the outlast is the color intensity column. So again the same thing here. Let us change the column name to color intensity. Let's run that and let us perform the same thing again. Here as well we will change the column names. Let's run that and let us check the shape here. So now it's 162. Fine. Now after color intensity, the last column in which we have outlast is hue. After that we don't have any outlast. So the last column here to handle the outlast is hue. Let's run that and let us even run this. Now we'll check the dimension here. Now it's 161. So in the final pre-processing, we have 161 rows and 13 columns. Let us display it once. Fine. So we have handled all the outliers now. Now when you again try to display this particular graph, let me just say again, I want to display this particular graph here. Let me rerun this. Now you can see, you can still spot that outliers here, but now they won't be that much in numbers. Let's say initially you had 10 outliers. Now they would have been reduced to 5 or 3. So they won't be eliminated entirely, but at least the number of outliers would be reduced. Fine. It's not that if you perform outlier removal, every single outlier from every single column will be removed. There still will be outliers, but just the number of outliers would be reduced. Now, as this is inbuilt dataset, it won't have any missing values, but still let us check for the missing values here. So let me say x dot is any dot sum. So as I said previously, it doesn't have any null values. Now we have to perform data normalization here. To perform data normalization now, we are going to use min-max scaler here. So let me import that from sklearn.preprocessing. I'm going to import min-max scaler. And then I will create an object of min-max scaler, which is scaler. Fine. Now I will say x is equal to scaler dot fit underscore transform. And here I am going to transform my initial data frame x. So basically what I am going to do here is I am going to transform the values from x dataset, from the initial x dataset, from every column of the dataset to a range between 0 to 1. Fine. When you just, let me say here, x dot describe. When you take the look at this particular table, you can see the minimum value and maximum value is different for every column here, which means every column of the dataset is on a different scale. So we basically want to bring all the columns onto one single common scale, that is between the range 0 to 1. And that is what we are doing here. So I am doing this fit transform both things in one single go. And if you want, you can do this both the things separately. So I will transform that values between the range 0 to 1 and again store that into a same data frame name x. And the reason behind providing this square brackets and colon here, if you don't provide that, then your transformed values will be stored in the form of arrays and not a data frame. And hence I have provided that. Let's run that and let us now try to display. So as you can see, now every value is between the range 0 to 1. There won't be any value greater than 1 or lower than 0. Fine. So we have performed data normalization here and we are done with everything. Now we just have to divide our data set into the training set and the testing set. And to do so, what I am going to do, I will import the train test split from sklearn. So sklearn.model selection. I will import train test split. And then I will say xtrain, xtest, ytrain and ytest is equal to train test split. Now here I will provide my input data frame, which is x, and my target data frame, which is y, and then the test size, which is 0.2, that is 80% data in the training set and 20% data in the testing set, and then random set is equal to 42. So that we will have same rows in our training set and testing set every time when we rerun this cell. Let's run that. And there's some issue here. Let's see what it is. So the issue is found input variables with inconsistent number of samples. Yeah, this issue is actually because when we remove the outliers, they actually just reduce the number of rows from our input column but not from the target. And to handle this particular issue, what we can do here, we can just go where we created our data frames here, and we just need to concatenate both this data set. So let me say here before that, x is equal to pd.concat, and here I will say x and my target frame y, and also axis is equal to 1. Fine, let's run that. Let me display the data set here. So as you can see, now we have a target feature here concatenated with the input features. So now we will again rerun all these cells here. Now before performing min-max scalar, what we will do, now that we have rerun all the cells and now we have equal number of samples into both our input and output data frame, if you want, you can just say input.shape here. And now even the target column is included into this particular data frame. So now we won't get this issue of inconsistent samples. But now we have to manually divide our dataset into the input and target feature again before performing min-max scaling here. So I will just say here input is equal to x dot drop columns is equal to target. By that what I mean, that I want to include all the columns from the x data frame into my input except for the target column, and then I will say y, which is our target feature or the target variable, and into that I will load just the target column. Let's run that. And now we have to perform this min-max scaling not on the x data frame but just on the input data frame. As we don't have to scale our target, we just have to scale our input. So let me say here input. Let's run that, and let me say here input.head. As you can see, now they are scaled, and now we can perform the train test split. Instead of providing your x, I will say your input. Fine, let's run that. So as you can see, now we are successful and we haven't encountered that error now. Let us check the dimension of xtrain now. xtrain.shape and xtest.shape. So out of 161 rows, our 128 rows are present in training set and 33 rows in testing set. Now we'll actually start building our model. To choose the algorithm, we can use the cross-validation score here. So if you want to choose out of various classification algorithms here, that is random forest, SVM, logistic regression, you have to choose the best algorithm here to build your model. What you will do, you will use the cross-validation score here. So you will basically say from sklearn dot model selection, you will import cross validation score here. Fine, and you will also import the algorithms that you want to evaluate your model upon. Let's say from sklearn dot linear model, I will import logistic regression. Then from sklearn dot ensemble, I will import random forest classifier, and then from sklearn dot svm, we have to import svc, that is support vector classifier. Let's run that. Now we will create a function here. We will say def validation. So I will just say validation, and here I will pass my estimator, that is the algorithm which I am going to estimate my model upon, then my input, and then my target. Fine, and here I will display cross validation score of estimator, then input, and then target. Let's run that. Let us call that function now, and here we will pass our arguments. So the estimator first is logistic regression, then the input is training set xtrain, and the target is ytrain. Fine, let's run that. Actually we have to return here, we haven't written anything. Let's run that again. As you can see, you are getting an array of scores. This is because it basically constructs 5 folds on your model and gives an accuracy for every fold. So you can take the mean of that. You can just say mean. Let's run that again. So the mean is, and you can multiply it by 100 to display the accuracy in percent. So when you use logistic regression, you are getting an accuracy of 99.23. Let us do the same thing on random forest classifier as well. Let us pass here random forest classifier and perform same thing. So when you perform random forest classification here, you are getting an accuracy of 98%. And then the last thing or the last algorithm here you have is your support vector classifier. So let us pass that SVC and then the X train and Y train. Let's run that. And when you make the use of support vector classifier, you are getting an accuracy of 97%. So when you compare all these things, you can see that you are getting the best accuracy of 99.23% when you make the use of logistic regression classification algorithm. So let us build our model using this particular algorithm here. So we will say model is equal to logistic regression, and then we will fit our model onto our training set. So I will say model fit X train and Y train. Let's run that. And after fitting our model, now we will make our predictions. To make the predictions, I will say model.predict, and here I will pass my testing set, that is X test. Let's run that. And these are all the predictions. So let us store these predictions into some variable. Let us name that as pred. Fine. Now we have to make the comparisons. We have to compare the original values with our predicted values. So let us display the first 5 true labels here. So the first 5 true labels are present in y-test. So these are the first 5 true values. That is, the first 2 have the category 1, then the category 2, then 0, and then again 1. Let us check what our model has predicted, which is stored in the variable pred, and we will again say the first 5 predicted values here. So when you try to compare, you can actually see your predicted values are exactly similar to your true values, which means your model is performing good. So let us now evaluate our model. So I will say from sklearn.metrics, we will import accuracy score, then the confusion matrix, and then the classification report. Let's run that. Let us try to print our model's accuracy first. So model accuracy score. Here in accuracy score, we have to pass the true labels which are stored in your y-test and the predicted values which are stored in pred, and multiplied by 100 to display the accuracy in percentage. Fine. So as you can see, your model is 100% accurate. Now this is because you had very less number of rows into this particular data set. Initially you just had around 185, and then when you performed outlier removal here, it got reduced to 161. So they are very less in numbers, and hence we are getting this much accuracy here. Fine. Let us now display the classification report. So I will say print classification report. Here I will again pass the true values stored in y-test and the predicted values. Let's run that. So as you can see, the precision, recall, FN score for every category here is 100%, and even the accuracy is 100%. Fine. So let us display the confusion matrix now. To display the confusion matrix, first we will say CF is equal to confusion matrix. Here I will pass the true values, then the predicted values, and then I will say normalize is equal to true. If you don't say this, it's still fine, but then it will display every value in the count, that is 28 times it's happening, or on 29 rows it happened. And when you say normalize is equal to true, it actually displays the values in percentage format, that is 100% times it's happening, or 50% times it's happening, something like that. Now to display the confusion matrix, we will make the use of heat map. I will say sns dot heat map. Here I will pass my CF variable, then a0 is equal to true. Display the values on the grid of heat map, and then the theme of heat map, which is crest. You can give any theme you want. This should be in single quotes. Let's run that. And this is your heat map. Now it just got that much big because initially you changed the font size for this particular box plot here. So let me again say, let me remove this, and here I will say before this thing, I will reduce the size. I will say 7 by 7. Let's run that. Fine, that's fine. Now on x-axis, let us also give the labels here. So plt.x label. On x-axis, you have predicted values, and on y-axis, you have actual values. Fine. And let's run that. Now, as you can see, this is your confusion matrix, and when you take the look at your diagonal, it's showing that 100% times everything is happening. That is, if you take the look at first dark blue square, it's saying 1 means 100%. It's saying that 100% times, that is every time it's happening, that the original category is 0, and your model is also predicting it to be 0. So for every category, it's 100%. So this was the confusion matrix, and now we have built our wine quality prediction model successfully with an accuracy of 100%. That's it for the video. Thanks for watching.